Example 3. A force ranger sights a fire directly to the south. A second ranger, 7 miles east of the first ranger, also sights a fire. Let's just actually start by sketching that, and then we'll read the last little bit of this. Okay. So let's see, we have a ranger first, and let's maybe call the first ranger Ranger 1. We'll just label him R with a subscript 1. And then there's some fire to the south, right? And it was directly to the south. Okay. And then there was a second ranger 7 miles east of the first ranger, so in this direction. And we'll just label this one R with a subscript 2 for Ranger 2. Okay. Now we have a little bit more information. It says the bearing from the second ranger to the fire is south 28 degrees west. Okay. So I'm going to just sketch in this right here. Now let's see what we can do with this bearing right here. The south 28 degrees west from Ranger 2 to the fire. This is where most people will make a mistake on this problem. So if we're trying to think about the bearing from Ranger 2 to the fire, it's actually helpful to maybe think about our south line here. We don't have to actually sketch this in here, but this is going to ensure that we don't make the common mistake. Okay. So the common mistake would be to put the 28 degrees in here. Okay. It's just naturally where we want to put it. Okay. But again, remember, we're supposed to measure bearing off the north-south line. Okay, so here's our south line, and we're supposed to go 28 degrees towards the west. Okay. So that means that this 28 degrees is actually right here, which means the angle in the triangle here should just be 90 minus 28. Right, and if we do 90 minus 28, that's going to give us 62 degrees. Okay, so that's what we'll put in here. Now, note, what are we trying to find? Okay. Well, if we look, how far to the nearest tenth of a mile is the first ranger from the fire? So we'd really like to know this distance right here. Well, we can figure that out now because we have the adjacent side to the angle 62 degrees, and we are looking for the opposite side. So let's set this up. If we have the adjacent and opposite side, that sounds like we're going to be using tangent. So I have tangent of 62 degrees is equal to TOA, right? Opposite over adjacent. So that's going to be D over 7. Okay. And to solve for D, all we need to do is multiply both sides of the equation by 7. So we get 7 tangent of 62 degrees is equal to D. Okay. And we're supposed to round our answer to the nearest tenth of a mile. So if you plug this in your calculator and make sure you are in degrees, we will get D is approximately equal to 13.2 miles. All right, let's go ahead and move to the next one. So now we're going to be looking at problems that we can break into multiple different triangles. And the idea is we'll be trying to find the side length of a triangle that's not a right triangle. But there will be other right triangles in the picture that'll help us maybe find that missing side. And so here's our first example. This one is just completely geometric, right? But we'll do some application ones here in a minute. So let's think about this. We want to find this side x, okay? And I will probably get rid of what I'm about to mark here, but you can see that this side x is part of this triangle that is not a right triangle, right? We have this obtuse angle here. So is what we're going to do is we're going to look at two other triangles. Let's maybe start off with looking at this big one here. And we'll find the length of its base. Okay, so is what I'm going to look for. I'm going to look for this length right here. And maybe let's call this length here y. Let's call it y. All right, well, if I want to find this length here, again, I have a right triangle that we've sketched. Okay, we have an angle in here. We have the opposite side. This actually sounds like tangent again. So if we took tangent of 20 degrees, that should equal the opposite side, so 500, over the adjacent side, right? TOA, so over y. Okay. And if we multiply both sides of this equation by y, we get y times tangent of 20 degrees is equal to 500, and then we could divide by tangent of 20. So we get y equals 500 over tangent of 20. And I'm not even going to bother to plug this in my calculator right now. I don't care about the decimal approximation for y. Okay? In fact, the side length we're trying to find, right, is x. Okay? So we found y. Well, let's see if we can maybe find another helpful side length. Let's maybe look at this triangle here. Okay. Well, if we were to find the length from here to here, maybe we could call this z. Okay. But the point is if you did y minus z, you'd be left with x. So if we can figure out what z is, we're done here. And so let's do the same thing. Our angle this time, it looks like it's 48 degrees. So tangent of 48 degrees is equal to opposite, so 500, over adjacent, which is z. And if we go ahead and we solve this for z, we should end up with z is equal to 500 over tangent of 48 degrees. And now we can get our final answer. We can figure out what the length of x is. Let's do that. I'll leave this z in here though. There we go. So if I'm looking for x, we're just going to do y minus z. And in your calculator, that'll just look like this 500 over tangent of 20 minus 500 over tangent of 48. And if we subtract those two, we get about 924 if we round to the nearest whole number. We weren't even given units here, okay? But it would more than likely be something in length. Okay, so meters, feet, kilometers, so on. All right, we have another one that I want you to try, but I want to sketch the picture for us first. And here's our picture. Okay. Let's fill in the rest of this. So we have the flagpole situated at the top of the building. The angle of elevation from a point on level ground 330 feet from the building to the top of the flagpole is 63 degrees. Okay. So we are talking right now about this angle here. That angle is 63 degrees. Okay. And then we actually have one more angle here to deal with. This is the angle of elevation from the same point to the bottom of the flagpole is 53 degrees. So this angle here is 53. And I should also write this in here. The base of this triangle, we were told, had length 330 feet. Okay. And now is what we're asked to do is find the height of the flagpole. Okay. And I will warn you before you try it, in this problem, the flagpole ends up being it ends up being a very tall flagpole. Okay. So don't be surprised if the number comes out kind of large here. But go ahead and give it a try, and in the next video, we'll go over this problem.